Hello, welcome to our 16th set of notes. It's a quick guide to bonding and naming. There is kind of a lot of stuff going into this one, so kind of bear with me as we go through it. The reader that you've already completed will kind of help supplement what's going on here as well. So let's get on into it. All right, so ultimately we're trying to figure out, why do bonds form? And bonds form to lower the potential energy between charged particles that compose atoms. Now, when you take a charged particle, such as an ion, because those are all charged particles, by forming bonds, they ultimately helps them get to an octet. Now, the charged particles is just one way of forming bonds. They don't always use ions. Some bonds do, some bonds do not. Again, potential energy is playing a role. And when potential energy is lower when two atoms are together than when they are separated, that's why another reason to support why bonds are forming. Because at the end of the day, energy is the currency of chemistry. Everything wants to be lowest energy. The potential energy is what is stored in the bond. So this lovely graph kind of dictates or shows, when you're over here to the far right, there we go, atoms are approaching infinitely apart as you go to the far right. But as you come closer and closer and closer together, we get the electron clouds are overlapping. Kind of looks like an owl, if you will. And then at some point, you get this lovely perfect distance. Now it kind of looks like a koala. Maybe you can see it, maybe you can't. But if we come down here, we reach the point of the graph that is the bond energy and the bond length. The bond energy seems to be negative. Well, that's what it's supposed to be. When bonds form, the creation of a bond between atoms, energy is released. That's why, as we just said, the formation of bonds might be of lower potential energy than if the atoms were infinitely apart. The bond length is the distance between the two nuclei. We talked about atomic radius. This is obviously double that because we're doing the entire bond length. The interesting thing here to note is, once you pass this happy perfect distance, where the bond energy and bond length are at the bottom of the red curve, if you go past it, the amount of energy it takes to actually get those nuclei closer and closer together goes up exponentially. Well, two positive nucleuses do not want to go together. That's why it takes an incredible amount of energy in order to force them together or fuse them together. Nuclear fusion, what's happening in our stars, in order to make that happen. So that's kind of why it's skyrocketing there very quickly. Now, if we look at a bond in its formation, we got a bunch of things going on. We have the nucleus and the electrons of one atom, and we have the nucleus and electrons of the other atom in our bond. As you can see, there are both repulsive forces and attractive forces trying to find an equilibrium, if you will, some place that they can coexist in order for the bond to actually occur. So electrons are going to repel other electrons, and we already kind of talked about the nucleus or the protons already going to repel each other. But then we have the kind of third factor of the electron proton attractive forces, as you can see with the green lines. Ultimately, when a bond forms, the electron proton attractive forces outweigh the repulsive forces. If two atoms for some reason do not bond, they do not form a molecule, well, that could just lead to the conclusion that the repulsive forces are greater than the attractive forces, and it wouldn't work out. All right, so let's head on into our types of bonds. First one we're going to look at is ionic bonding. Ionic bonding ultimately comes with the transfer of electrons. They create these charges. As you can see by the image to the lower right, sodium has 1 valence electron, chlorine has 7 valence electrons. When they get close to each other, sodium becomes a positive ion and chlorine becomes a negative ion. Basically what happened, chlorine took the electron away from sodium. Why? Electronegativity. We've talked about this trend, and we've talked about what electronegativity is. So because of chlorine's very high electronegativity and sodium's very low electronegativity, chlorine is able to rip the electron away and create a negative ion for itself, and making sodium become positive. So the electrostatic bond is basically an attraction of opposite charges. The positive is attracted to the negative. They are not sharing the electrons. These 2 electrons that are kind of right between the 2 atoms that I've highlighted with the mouse, they're not being shared. Chlorine owns them. Sodium has no bearing to it. So again, it's just a positive and negative attraction. All ionic bonds are created when you have a metal and a non-metal. So if you're looking at the periodic table, if you pick something from the metals and something from the non-metal, if they can create a bond, it'll happen. But again, ionic bonds are metal and non-metal only. Here we have a couple examples of monatomic ions, calcium and oxygen, one type of element that makes up its ion. We also have polyatomic ions. Now the interesting thing here is everything here on the screen with polyatomic ions, they're all nonmetals. But wait, you just said only metals and nonmetals create ionic bonds. In the case of polyatomic ions, notice NH4 is made of nitrogen and hydrogen. SO4 is made up of sulfur and oxygen, poly meaning many. Because these are ions, they can form an electrostatic attraction to make an ionic compound. So only if it's a polyatomic ion can you have all nonmetals, but in generally speaking, all ionic bonds are metal and nonmetal. All right, our covalent bond. So here we go. As you can kind of see with this diagram, it looks very different than the one we just saw with ionic bonds, where the electrons are kind of doing something different. So because the electronegativity values are closer together with nonmetals, as you can see, carbon and hydrogen, both nonmetals, they cannot fully transfer the electron. Well, they have to then share the electrons. And electronegativity is going to play a big role when we get into polarity. So make sure you understand electronegativity and the role it plays between atoms, because when it comes to polarity, it's going to need to be accounted for. So all covalent bonds tend to be nonmetals and nonmetals. Carbon, hydrogen, both nonmetals. So it's kind of easy way to figure out if something is bonded as a covalent bond or if something is bonded as an ionic bond based on the chemical makeup or the constituents that are used to put it together. Now, from a covalent bond perspective, continued, we have a little chart here illustrating hopefully some trends. Let's take a moment and see if we can identify any trends. Okay, so hopefully you looked at the number of bonds up here, single, double, triple. As we increase the number of bonds, notice what happens to the length. The length decreases. And as we increase the number of bonds, look what happens to the energy. The energy required to break that bond is going up. Now, for any given bond, a single bond is just 2 electrons. So a double bond would be 4, and a triple bond would be 6. Well, the more electrons that you have shared between 2 atoms or their nuclei, the greater attraction you're going to have. That's why the bond length gets smaller. Well, because you have greater attraction, the amount of energy to break it or rip it apart has got to go up. So if you look at all these sets of single, double, triple, you're going to see the same kind of theme. As the length gets smaller, the energy goes up. All right, our last type of bond deals with metallic bonds. Now, the electrons basically detach from the atoms. They're not transferred, they're not shared, they're just able to kind of free flow move around. And we get this idea of the sea of electrons. If you look at the sea, it's always moving. These electrons, the little purple dots, are always moving in and around the metal sample. Now, metallic bonds are only metals, clearly, because the root word of metallic is metal. Should make sense. All right, let's see if this is going to work. All right. Well, that's unfortunate. We don't have any volume. Alrighty then. Not sure why that didn't work, but hopefully you saw, again, an illustration of the electrons free flowing and kind of moving around every place they need to go. Obviously, you can come back and watch this. Maybe you heard it. I did not. All right, so ions. Reminder, print your ion sheet. It's in the reference section. Now, when we work with ions, we got cation, we got anion, things we've already talked about. Nothing new there. Again, your ion sheet has a list of most of them, not all of them. When you look at it, you'll kind of see what's going on. You have monatomic ions. So again, as we kind of already said this, they consist of only one element. All monatomic ions are on the periodic table. Every single one of them monatomic. When we deal with polyatomic ion, you have to have an ion with 2 or more elements, as we said earlier. So cyanide, Cn minus, and the sulfate ion, SO4 2 minus. Polyatomic ions do not exist on the periodic table. They exist on your ion sheet, or at least the ones we expect you to know. Now, if you can do me a favor and go grab a periodic table, maybe pause this while you go get it, and then come back so you have one that you can write on. So here we are. We want to predict ionic charges of single atoms, i.e. monatomic ions. Everything in the column 1 loses 1 electron. We've already talked about that from how ions are formed. So they all form 1 plus ions. Group 2, they all form 2 plus ions. Group 3, 3 plus ions. Group 4 or 14, again, they can lose or gain electrons. It kind of depends on what they are going to be bonded to that will control what's going on. Group 15 or 5, again, they gain 3 electrons to form 3 minus electrons. Group 16 or 6 gains 2 electrons to form 2 minus. Group 17 or 7 gains 1 electron or 1 minus. So looking at a periodic table, you always know what type of ion is going to form based on the column it's in, because the ion tends to go with the number of valence electrons and its reference to becoming a full octet, losing or gaining electrons. Our last group, the noble gases, we've mentioned this a billion times. They don't react. They don't do anything. They hang out. They're cool. They're chill. So they don't form ions. Now, this big group in the middle, the D block, from way back when, the transition elements, they can have more than one possible oxidation state, meaning they can have multiple charges. For example, here there's iron 2 and iron 3. Other ones have other different charges, but notice that in the name here, it's shown the Roman numeral. If I'm asking you questions about elements in the D block, for most of them, I have to give you the Roman numeral. The Roman numeral is the charge. Now, quick side note, there are a few listed here: zinc, silver, and cadmium. They only have one possible charge, meaning I will not give you a Roman numeral. So these three you kind of just need to know. All the other ones, you're going to be given a Roman numeral in order to know its charge for the purposes of writing compounds and writing names. Well, let's get into how we name these lovely bad boys. So when we name things, we're going to do cation first and then the anion. Always, every single time. And no, you're not going to have a comma in there. You just write the name of the cation, then the anion. So if it's a monatomic cation from the periodic table, you just use the name of the element. Calcium 2+ is just a calcium ion. And if it's a monatomic anion, we take the root word and we end in "ide." So here's chloride. That's why table salt is called sodium chloride, not sodium chlorine. So all monatomic anions end in "ide." So we put the two together and we get calcium chloride. So if I gave you CaCl2, you would write calcium chloride. Now, when it comes to polyatomic ions, they always keep their kind of special name. You're not going to add the "ide, you're not going to do this or that. You just go with what the name of the ion is. So potassium is just a monatomic ion. It's potassium. And PO3 is the name phosphite. It's on your ion sheet, so you can look for that. But again, pretty straightforward when we're dealing with ionic compounds, metal and non-metal. It's just potassium phosphite. Just name each ion. Now, when it comes to metals in that D block that we have to deal with, and some outside the D block as well that have multiple charges, this is where we have to use our Roman numerals. So if I look at lead chloride, PbCl2, right here, I know lead is my cation and I know chlorine is my anion. So it's lead 2 chloride. Now, how do I know it's a 2? Because lead could also be a 4. Well, chlorine is in column 7, which means it's a 1- charge. From that perspective, if it's 1- and I have 2 chlorines, therefore it adds up to a 2-. When we look at ionic compounds, the overall charge must be 0. So if I have 2 negatives from the 2 chlorines, 1 from each, I need 2 positive from the lead. So that's why lead 2+ matches 2 chlorine -1s and gives me my lead 2 chloride. Next example, iron oxide. Oxygen is in column 6. We know oxygen has a -2 charge. Well, there's only one iron written here. So if oxygen's -2, iron has to be +2. Now I know its charge. Therefore, my naming, iron Roman numeral 2 oxide. So kind of keep that idea in what's going on. Now, again, let's kind of look at it one more time to make sure we understand what's going on. We want to work backwards, so to speak, to determine what is the charge on the metal. So here's my FeCl3. I'm not too sure what the iron charge is yet. Chlorine, there's 3 of them. Each of them have a 1- charge. So that adds up total to a -3 charge. Well, if it's -3, notice iron, there's only 1 in that formula. It has to be iron 3+ to balance out the 3-. Rewrite it, I get iron 3 chloride. Another example, we have Ni3N2. Well, nickel, not too sure what its charge is going to be. Nitrogen, N2, there's 2 atoms. Each of them have a 3- charge, according to the periodic table. So 2 times the 3- is going to be a 6- total. Well, I have 3 nickel atoms in my formula, and they have to balance out a -6. So what must each nickel individual ion be? Boom! Yes, it is. It's a +2, because 6 divided by 3 is 2, and we know it's a cation, therefore it has to be positive. Rewrite my answer as nickel 2 nitride. Remember, nitrogen is a monatomic anion, so instead of being nitrogen, it's just nitride. All right, naming covalent molecules. We just finished looking at ionic. Now we have to do covalent. Now, the prefixes here on the right, I'm pretty sure we all know them. They also should be listed on your ion sheet as well. So, naming covalent molecules, obviously it's 2 or more nonmetals only. All elements keep their normal names, except the last element ends in "ide." So covalent molecules kind of a little easier to name because it's the full name of the element, except the last element ends in "ide." We got to use these prefixes, mono, di, tri, and so forth, for both elements, if there are more than one. But we never use mono for the first element. So think back to that stuff that comes out of your car. It's carbon dioxide, but it's also carbon monoxide. So the mono is only used for the second element, or the last element, but mono is never used for the first one. All right, a couple other quick things. Double vowels, pain in the butt. We don't like double vowels because they're just a pain in the butt and they don't really make sense. They sound weird. So we drop the last vowel from the prefix portion of the name. So a couple quick things. Any double vowel with I is okay. So diiodide. That one's fine. You want to keep that. Pentaiodide. So the A and the I are double vowel, but that's okay. Monoiodide. The O and the I. That's fine. But monooxide, that doesn't work. We don't put 2 of the same vowel together. So it's monoxide, like in carbon, monoxide. All right, so a couple examples. Our first one is P2O5. Di is in 2, phosphorus. Pent, oxide. Notice we dropped the A. It's not pentaoxide, it's pentoxide. CO2, carbon dioxide, you're familiar. I've been mentioning CO for a couple times here now. Carbon monoxide. And N2O, dinitrogen monoxide. Notice we dropped the O in mon for monoxide. All right. Now, naming metal substances is pretty simple. Just name the metal. Just name the metal. The end. It's Cu. It's copper. That was pretty simple and straightforward. Yay. All right, few odds and ends. Are there exceptions? Are there weird rules? Yes, this is chemistry. There always are. Just get used to it. One of them being our diatomic elements. Some elements come as pairs and do not exist by themselves. So these elements in this mnemonic device, horses need oats for clear brown eyes. All these elements exist in nature diatomically. You're not going to find any of these single atoms hanging out. They can be bonded to other things, but for getting, hydrogen, nitrogen, oxygen, and so forth, they exist as diatomic elements. No other elements on the periodic table are diatomic. Only these ones. So again, memorize the mnemonic device. Horses need oats for clear brown eyes. All right, any more exceptions? Yeah, probably lots. I just can't think of them right now. It's been a while. But again, as they come up, we will talk about them and we will work them out to see how to utilize them. But again, exceptions do exist. So don't freak out when things don't necessarily follow the rules. It's an exception. All right, thank you very much. If you have any questions, please write them down and bring them to class. Thank you. Have a good one.